All right, we're recording. I hope you don't mind being recorded. It's just for our own community. If you're not in our community, be sure and send me an email and I'll send you an invite. So Serena, I don't know if you are, but if you're not in the Mighty Networks community, send me an email. I'll send you the invite for that. The classes are always here, and the discussion and the resources and assignments and videos are always there. Every day, Tuesday, Wednesday, Thursday class, you can go and then look at the top for videos and you'll see the videos. And the Thursday video is always the best because the first 2 days I screw it up a bunch and I'm practicing, but the Thursday one, I usually finally don't get it too wrong. So don't watch Monday, Tuesdays, or Wednesdays. Always watch the Thursday video. All right. Any quick comments from last week from the 4.5 billion? No, that's fine. All right. Yeah, we will get more into this stuff, so there will be plenty of questions and comments. To start, I'm going to ask some questions. Remember, I don't ask stupid questions. So if it sounds like a stupid question, it's meant to make you think. Okay, first question is, how many people have ancestors who were Black? Ancestors who were Black. What's an ancestor? What? I don't see any hands going up.
I suppose there's a theory everyone came from Africa
Yeah.
There's no
initially.
theory. There's no theory. Everybody came from Africa.
So therefore, all of us.
So all of us have, if you go back 10,000 generations, all of our great-grandparents were Black. I'm sorry, and your grandmother too. They were all Black. White people were probably invented around 25,000 years ago, although it's debated, but that's the figure I would take. And so I'm trying to get you to think more in concrete terms and in definitions and in precision. So another one is, how many people have an ancestor who was a fish? Right, your 20 millionth great-grandfather was a fish. And your 20 millionth great-grandmother was also a fish. And all of those species, all of those animals from fish to humans, bred with other animals of their same species. How could that happen? Well, read Richard Dawkins if you want the true story. But the short answer is that genetic mutation happens very slowly, and there are transitions where subspecies can interbreed and speciate and then have mutations, but there aren't any big sudden changes. They're all very gradual. And I think people kind of like picking up little extra science here and there rather than being super deep on climate. Is that right? Or do people, how many people are really hardcore, just wanted to spend all their time learning climate? A few maybe, but I think most people are happy with a mix of science and climate. Yeah, good. Cool. All right. If the sun is the size of a basketball, how big is the Earth and how far away is it? The sun, let's just say 12 inches diameter. How big is the Earth and how far away is it? Who wants to throw out a guess? Michael?
I'd say like a grain of sand.
Grain of sand.
And about from school, I would have said it was 93 million miles away.
Well, no, that's in reality.
Oh, okay. So,
it is 93 million miles away.
right.
But if it's a grain, if the sun is a basketball, how far away is?
Oh, okay. So,
yeah.
Half a meter, half a yard.
1 grain of sand about 18 inches away.
Yeah.
Ish.
Yeah,
Anybody else? It's a
that's a bit
brave
close.
guess.
Actually, I'll double that. I'll go for a yard.
A yard, a whole, he's going for a whole yard. All right, who's next? Anybody else? Any science types? Come on. It's okay to be wrong. I'm always wrong. I'm used to being wrong. If you want to learn everything, you're going to be wrong 99% of the time. So get used to it. One more guess? Come on. Let's have it. James, Joe, Tanya.
I was going to say maybe a little bit bigger than a grain of sand, but I was trying to think of something that was smaller than a blueberry, but not as small as a grain of sand. So
Okay, that's fine. I'll give it to you. It's a peppercorn.
okay.
Peppercorn is about 2.5 millimeters or so. Let's go with that because that's right. And now how far is it? How far away is it?
100 meters.
Is it a yard?
2 meters.
No.
I'll go.
2
100
yards?
meters.
Do I hear 5, 10,
100.
100 yards? It's 100 feet, 30 yards. 100 feet, and it's the size of a grain of a peppercorn. Now, let's just stick with that same theme. Now the Earth is now 6 inches around. How big is the sun and how far away is the sun? Six inches. How big is the sun and how far away is it?
Gone in a P, and now 50 foot.
Well, it's not a P to the sun. This is the Earth is 6 inches. How big
Oh,
is the
okay.
sun?
Okay, I'm not getting this. Sorry.
Yeah. How big is the sun and how far away is it?
Ooh.
300 yards.
300 yards. Okay. Anybody else?
I can't think anything that big spherically that I can describe to you.
Well, what's the diameter in feet, meters, something?
Okay, I'll just go at a guess 50 meters.
50 meters, fine. Anybody else? If the because I think everybody's in the UK, if I'll use imperial, if the Earth is 6 inches, the sun is 50 feet, about a three-story house, about a fire station or so, and it's a mile away. So
About
the
1,000
Earth
feet.
intercepts a tiny amount of the outgoing radiation of the sun. It's much less than 1%. I don't think it's 1% of 1%. Okay, it's a tiny amount. Yes, it's huge for us. And it just happens to be about the right amount for us to live. And please keep in mind, there's no Mother Earth. There is no thing that controls and keeps the Earth in some habitable zone. If the Earth gets hit by a meteor, its orbit gets put off and we go spinning far enough away from the Earth, everything will just freeze. The Earth does not care about us. There's no magic feedback that keeps us in the zone at all. We're just lucky that it stays in the zone. And in 500 million years, the oceans will boil and the sun will eat the Earth. So, nothing cares that we're here. Next. What's the difference between 500 million and 500 million?
I'd say they're the same. There's 2 different billions, though, isn't there? There's 1,000 million.
What's the difference between 500,000? Did I say 500,000 and 500 million? Sorry, I think I said it wrong. 500,000 and 500 million. It's just simpler this way. What's the difference between 500,000 and 500 million?
Is that not the same?
Who thinks they're the same?
They're the same.
Yeah, they're absolutely not the same. Not even close. I mean, if I said that something is 500,000 units, what does that mean? Exactly 500,000.000? It doesn't mean that at all. It's got 6 zeros on it which means it's between 400 and 600,000 somethings probably. It certainly, if I said it's between 490,000 somethings and 510,000 somethings, that'd be too narrow, right? Because it's, 520, 530, that's all in the 500,000 range. Okay. But if I said something is half a million, well, now, it's 400,000, it's 350, 380, it's bigger, right? And now if I told you that something was 511,111 units, in other words, all those zeros change to one. Well, what does that tell you? That's between 511,110 and 511,112, because it's very precise. That's 6 digits of precision. If I told you 511,111, that is so precise that it's going to be within 1 unit either way. Because if it weren't, I would have added that unit, right? Because that last 1 digit is meaningful. Whereas if I say 500,000, those zeros are not nearly as meaningful. It's not the same at all. Okay? Those zeros are placeholders and they imply a range. And generally when we hear 500,000, you should hear, well, okay, between 400,000 and 600,000, somewhere in there. I wouldn't be surprised if it was, 580,000. I really wouldn't. Okay. Depends, of course, on the context of our conversation, but nobody ever means 500,000.000, right? Okay. So these definitions really matter. And you'll see as we go along that the definitions and the context matter a lot more than the actual words. Okay. Now, real quick, and then I'll get into some presentation. What is a conspiracy theory, or who is a conspiracy theorist?
Well, I'd argue the word conspiracy just means, a group of people got together and decided to do something. So fairly general term, but I believe JFK was the coining of the term, with the different theories that are bounded from that.
For his death?
Yeah,
okay.
The CIA involvement, or Lee Harvey
I think
Oswald.
the CIA came up with the term, but I'm told, I don't know. What is a conspiracy theory? Or what is a conspiracy theorist? As the CIA, I believe this, and I don't know if it's true, but I'm willing to believe it, that the CIA, invented it as a kind of a convenient handle to use to call people, so that if you call someone a conspiracy theorist, you lump a bunch of theories in and pour them on top of one person. Something about COVID, and something about assassinations, and something about the deep state, and tinfoil hats, and aliens, and and a whole bunch of other things. That is really a convenient weaponized term, to call people a name that to lump them in with people who believe obviously fake stuff, like the moon landings were never true, or the earth is flat. Well, then you must be one of those idiots if you say that maybe the COVID vaccines aren't as good as we were told. Because it's just shorthand for, oh, well, you're a conspiracy theorist. You're not a thinker, right? You're not a critical thinker. You just go with those alternative wacky people, right? But it's really just a way to say, well, you're not one of us, and you're not good. Without me putting any effort into it, I can just call you that, and it puts you back on your back foot right away, right? And so it's really for dummies. In fact, because in the real world of critical thinking, you have to take each thing on its own merits. And for example, some vaccines work, and there's really no question about it. And some vaccines really don't work. Once in a while, for example, the CDC gets the flu vaccine wrong, and it doesn't work, and we have a pretty big flu season because the vaccine failed. That's, you know, so, and some years they get it right and they do a great job. So, you know, some work, some don't. The details matter, and every individual situation is different. It's the same with climate denier. I've been called a climate denier for so many years, I can't count. And it's just a way to weaponize words to lump you in with other people who don't think about things. It's just a way to avoid thinking and to categorize people. And it's the same with Republicans and Democrats and, you know, Tories and Labor, just a way to, you know, conveniently attack people with shorthand without doing any work. Okay, so these terms really are negative, and you should call people out when you hear them say them. Anything like that, any of those convenient handles, you should just call people out and say, well, so, you know, what do you mean? Can you break that down a little more? Can you be specific? Because they usually can't. And I can guarantee you, the more you learn about climate, the more pissed off you'll make other people, because they don't want you to be right. Because that would mean they're wrong. They do not want this. You know, you took a class from a guy named David Siegel, and now you're a climate expert? Really? You know, oh, you've been spending too much time on the internet, and I've got, you know, the United Nations and Yale University and Columbia and the World Economic, I've got all this 97% consensus against what? Some, you know, some internet's conspiracy theory denier stuff. So it's not going to help you. It'll make you more frustrated because you'll know for sure that these people you talk to don't know anything. But they don't care that they don't know anything. It's the important thing to them is that the world is on fire and humans are destroying the earth. And a lot of people make a good living doing that, in case you have seen my video on that topic. But people just want to be members of their tribes and don't want to be ostracized, and so they can't do independent thinking. So now I want to run through a few units, short things that presentations, and then we're going to stop for a minute, but I'm going to take you through some concepts and then go a bit back over last week to review quickly. So all I have to do is find where there we go, share screen. Any questions about that the last 10 minutes? Anybody? No? Everybody has Black ancestors now? Good? Great. Everybody related to fish now? Perfect. Amoebas? Sorry, but that's where we came from. Here we go. This is my deck full of stuff that I presented it to you. We'd be here for about 6 months. There's too much material for me to show you in just 12 weeks. So I want to break it into short topics. This is why I decided to teach the class, was to put this together better, because it was all very loose, and I'm starting to put these into little short formats that I can then record and make a bunch of recording, like 100 small recordings that can then live on a system like we have for our community, and then let people into that so they can see all that stuff at their leisure, and then the classes can be conversations. So that's where I want to take this. And so the first one is what is climate? And it's a tough thing to define. So the key to understanding the word climate is that it's more about the period than the exact thing we're measuring. Yes, we talk about temperature a lot. We talk about Earth's average temperature, which is a silly number. We should never be talking. If you want to talk about over 10 million years, sure, that might have some relevance, but today it's just a convenient attack word to use. It's a weaponized word. But when we talk about climate, I want to show you that anything, whether it's weather, clouds, temperature, extreme events, whatever it is, it doesn't matter if it's on the order of 10 years. 10 years is not long enough. So this is a 10-year yardstick. And if you took this is the temperature over about 20 stations, weather stations in New Hampshire, starting in 1895, because they have long record keeping there. And if you took a 10-year yardstick to any of this, you wouldn't say you can see a trend at all in 10 years. It's easy for the trend to just reverse in the next 10 years or 5 years. It's very jumpy, right? So we don't talk about 10 years in the climate game. We talk about generally 30 years or longer, that you want to talk more about a climate regime, something that is changing or trending. Is it really a trend? Well, it should be a trend for at least 20, and even if it's 20, it can reverse for another 20. Is that climate? Well, it's borderline climate. But here for 30 years, we see in the United States temperatures going up in the 30s. This is something that a lot of temperature graphs won't show you very well. They manipulate the data to make it look different. This is actual raw data from thermometers in New Hampshire. And then we have 30 years where temperature is going down. And then we have 30 years where it's going up for sure, till the early 2000s or so. And then really since about 1998 or so, it's been very flat. And those are the kind of regimes and trends that we see. And then obviously CO2 or whatever other thing is going up the whole time. And it'd be hard to believe that it's creating this. And then there's a lot of explanations and kind of backflips and somersaults to show, yes, it can actually happen. It's really going up, but it really isn't going up. It's going up a bit. But it's hard to know what's driving this. And that's what real climatologists try to figure out. And it can have to do with humidity or, other types of, tropical storms and other types of things to measure. But generally, we talk a lot about temperature when we talk about climate. Now, I want to, again, and this is going to be new for some people, but mostly anybody who's seen my talk with Mike will be familiar with my distinction between temperature and heat. What is temperature? Anybody? What is the definition of temperature? By the way, I can't see you. I can't see most people, so just unmute and say.
The rate of the movement of molecules?
Yes, it's the velocity of molecules. As Richard Feynman said, temperature is molecules jiggling. It's a Feynman technical term. And it's really what is the speed of the molecules as they jiggle. And all the molecules in your body and in your house and in the atmosphere are all jiggling, and they're all going various speeds depending, but a lot of them are bouncing into other molecules 1 billion times a second. They all travel at some high speed that's related to the speed of light. And that's what keeps a balloon inflated. It's the temperature, it's the speed, it's the interaction between the fast moving molecules that keeps a balloon inflated. And so temperature is really just speed of molecules. And this is why I discussed this with Mike. When you're out in deep space in between galaxies, there isn't any direct sunlight. You just have occasionally, they have about 1 hydrogen molecule per cubic kilometer out in deep space, roughly. And when it gets hit by a photon, which it does because starlight is photons, right? It gets accelerated because the incoming energy is tremendous. And the molecule is very light. So a molecule in space can be very, very hot, can be 5,000 degrees centigrade out in the middle of space. Because remember, you can only measure molecules. That's what heat is, or that's what temperature is. Space has no temperature. Only molecules have temperature, and atoms. So these molecules out in deep space are really hot. Often 5,000 degrees, because they're getting slammed by these photons, and that can really move these things away from the sun. That's the solar wind. And it's very powerful if you're a molecule. It's not very powerful if you're an astronaut in a spacesuit. But if you're a molecule, it's very powerful and you can be very hot. On the other hand, what is heat? If the temperature is the speed of the molecules, what is heat?
Think of it as kind of like a radiant wave to some extent.
And those are long wave photons. That's infrared. Those are still photons, but the heat. Remember, we had a conversation with Mike. Most people remember this, where you turn the oven up to 99 degrees Celsius and you let the whole thing come up to 99 degrees. If you put your hand in the oven and feel the air is 99 degrees. Okay. Everything in the oven is 99 degrees, right? It's okay. You're going to be all right. It's not going to burn you. But if you put your hand in the water, you're going to get burned, right? Because the heat, 99% of the heat in this oven is in this water. 99%. It takes 100 times longer to heat the water than it does to heat the air. And so the way to think of heat is the number of molecules times the temperature. So if you have something at 50 degrees, and then you double that thing, you double the number of molecules at 50 degrees, you haven't changed the temperature one bit, but you've doubled the heat. Does that make sense? So the heat in the atmosphere is relative to what's in the atmosphere. And if you take, for example, where do I have it? Which has more heat? Desert air at 110 degrees versus humid tropical air at 90 degrees. Where's the heat? This would
Humid
be
tropical air.
Fahrenheit. There's more heat in the tropical air at a lower temperature. Yes? Everybody see that? If it's really humid, then it's more dense and there's many more molecules. And so there's a lot more heat in the tropical, humid, moist air. Okay? That's temperature and heat. Does anybody have any questions about this? These are just little 5-minute lessons. Questions about temperature and heat? No? Okay. All right. So it takes a lot more work or energy to heat a moist atmosphere or an ocean than it does to heat dry atmosphere or land. A lot more. So we're going to be getting into that later. Now I want to talk about coincidences. A couple of years ago, 2021, Canada hit its highest temperature ever, 50 degrees Celsius. You'll recognize that I'm big on uncertainties. Nobody knows exactly what the temperature is. It's just somewhere around 50 degrees. Okay. And why? What could possibly have caused it? It's obvious that it is humans emitting CO2 from smokestacks and tailpipes. Isn't it obvious? No?
Just explaining what these concepts
mean. Look how much cooler it is up in Yellowknife. Is there less CO2 in northern Canada than there is down here? Is there less CO2 here? No, this doesn't have. So you could say, well, okay, no, that's fine. It's the water. It's the greenhouse effect of the water in the atmosphere, because water is such a potent greenhouse molecule. Well, no, this is not a map of humidity at all, right? In fact, it's Canada and it's summer. It's pretty dry anyway. What's going on? Well, this is obviously a 1 in a million years event. And so it's got to have some explanation. So it has to be humans emitting something or some terrible thing humans have done. And this is the payback for our evil ways, because it's never been seen before in human memory, which isn't very long, right? So let me put this in context. because this stuff makes headlines around the world, right? You may have seen this headline, Canada's hottest summer ever, blah, blah, blah. We see it all the time. And it's because magazine and newspaper editors and website editors can't remember what happened 200 years ago. They weren't around. So this is just obvious that this is proof that humans are changing the climate. Now let's take another situation. Oh, sorry. The truth about that situation is that there were 3 effects going on, probably more. One is the heat dome. Heat domes are actually very common in this part of the world. They're very common in Oregon and Washington and even California. A heat dome is where you have cold air trapping heat, and it builds up, and it can build up for days and even up to a week. It can be insufferably hot, but there's cold air on top of it. So that negates the whole CO2 process right there. It's just being sat on until by heavier air until something moves it. Okay, there's no wind during a heat dome. Then there was an atmospheric river that fed it from the Pacific, and at the time there was the beginning of reduced albedo, and so more sun was getting in, more sunlight and energy was coming in, and about 20 other factors that all contributed to this 20 things that are actually fairly likely, but unlikely to all happen at the same time. It's not exactly a 1 in a million year event. And I want to show that by talking about cicadas. This spring in the eastern and southern United States, we're going to have a cicada apocalypse. Do you have cicadas in the UK? I think you do. A few once in a while. You don't?
Not many. I've never seen one.
Well, either they exist there or they don't. I don't know. But cicadas are very loud and very annoying, and they pretty much eat everything. They eat all the leaves off the trees. This spring, we're going to have the cicada apocalypse. Cicadas, some people don't know this. Cicadas bury underground for some number of years. Then they come out, they eat everything, they mate, and then they lay eggs back in the ground, and they stay underground for that same number of years every time. It's the same rhythmic pattern of number of years. And the number of years is always a prime number. Cool, but why? Why is it a prime number? Anybody? There are different broods, and the one brood is 5 years, one is 7, another one is 11, one is 13, one is 17. They're always prime. Nature has designed this so that when they come out, they're least likely to encounter another brood at the same time. So they can just eat the tree, and then the next year, another brood that's on a different timing comes out and eats the same tree. You see, so they have fewer coincidences to come out at the same time. If you were on even numbers, you'd have too many broods coming out at the same time competing for the same resources, and they would die out. So naturally, evolution chose selected for the ones that came out every prime number of years. And this year is the 13-year brood and the 17-year brood coinciding. The last time that happened was 221 years ago, 1803 or 180, whatever it was. And back then, the skies were black with cicadas, and they ate everything, and it was impossible to think or to get anything done. And this is right at the time of the new nation of the United States, when they were trying to, write the Constitution or the Bill of Rights. It was just a tremendous invasion that lasted about 3 months. And we're going to have that again this year. And people are going to blame it on climate. They are going to blame it on humans, because humans deserve these terrible pests and all the biblical turmoil that will be thrown by Mother Earth, trying to get the humans back for doing all this terrible polluting that they've done. And sure enough, it is going to be very bad. Right here, we're going to have dead maybe by the time our classes are over, we'll have dead cicadas flying into the windows in my building, because there will be trillions of cicadas. Now, people say, well, that's not right. That just never happens. That's a once in a million year event. No, it's a once in a 221 year event. It happens like clockwork. You can count on it. And it's really just 2 a 13-year and a 17-year event, which is pretty common, just lining up. People can't remember 221 years ago, so they say, oh, this is witchcraft. We must find the witches responsible for this and burn them. There's no science here. There's no, you're going to see it in the headlines. Once in a 1,000-year event, they'll just make up all this stuff and they'll say it's obviously because of humans. And then upon a little more inspection, everybody will realize that it's just 13 times 17 and it's not a big deal. So watch for coincidences because they explain a lot of extreme events. Even though humans can't remember them, when you learn that there's a very bad ski year in the Alps or there's hardly any snow cover in the Alps, yeah, okay, but you're forgetting 17 years ago there was tremendous snow cover. And, 12 years from now, there's going to be tremendous snow cover. It's just variance. It's nothing that it's just, so what? It happens more regularly than you think. Now we're going to do a fun unit called chaos and order. First, I want to talk about chaos. If you stand on a bridge over a river with 10 basketballs and you drop one basketball exactly in the same place every 10 minutes, 10 times in one afternoon, and then you come back 24 hours later, where are the basketballs? "24 hours later, are they 10 minutes apart each, 20 miles downstream? Are they? No, where are they? Where are those 10 basketballs?
All over the place. Don't know
All
context.
over the place is the correct technical answer. They are all over the place. A couple of them are bunched up. One or two are way downstream. Some are pretty far back. Probably one out of those 10 is stuck against a rock or under a branch or on a beach somewhere. It's impossible to model this because the chaotic flow of a river consists of many small boundary events where there is chaotic activity of the water that then is unpredictable. And if you add up, 50 such unpredictable things, you get a very unpredictable outcome. So this is stacked unpredictability or error accumulation. Okay, error stacking. There's no way to say the only thing you can say is that they're not going to be evenly spaced or anywhere close to evenly spaced. It's not possible with all the money in the world. You can't model where those basketballs will be. Okay, you can't say with any degree of confidence where those basketballs will be. And that's true for many situations that involve chaos. And here we have a lot of small chaotic activities building up, right? And here we have one that I talked about last week. The sun came from a supernova of a previous star. I was wrong. It didn't. It came from several supernovas of several stars. We don't know how many. And those supernovas created a gas and rock and dust cloud that we now call a stellar nursery. We can see them out in the cosmos. And many of those elements are above in the chart, in the periodic table, are above carbon, which means they can only have been made in supernova star explosions. It's the only time you get those elements. And these are elements like most of the metals, the inert gases, the radioactive. There's, everything above carbon. Carbon's number 8, I think. And so you've got most of the elements that make up us came not from our solar system, but from those stars that exploded before. And there's no way we could exist without them. So if you think about it, if your first star that comes out of the initial birth of the universe can't possibly produce complex life, you need a bunch of supernovas to create the elements that can then be combined into the elements of life. And what happened was a very chaotic event. So I want to I'm just going to skip to it. That in a supernova, here's a supernova cloud. It's an extremely chaotic event like most explosions, after which you can map and chart all of the little particles, and they are just pretty much going on momentum wherever they go. And you can model that. The chaos is out, and we're now into an ordered, directional stream of particles that you can model and figure out how they're going to then coalesce. And when enough of the helium and hydrogen molecules get together, you start to have an accretion ball, which attracts more and more molecules or atoms. And at some point, you get enough hydrogen again, because this is the second time that a new star ignites. This is all predictable. And then the rock cloud that goes around it turns into, things start to spin, and then you get a plane, and then they start to accrete, and all these little eddies start to form planets. It's pretty predictable. The actual eddies are a bit chaotic, so there's some chaos there, but it's pretty predictable that you're going to get some number of planets. And then once the planets get started and they start to accumulate, it's very much momentum. In other words, if you knew the position and velocity and mass of every particle, you could model it and say where this protoplanet is going. And then after a little bit of time, some asteroid comes and smacks into it, and then they have another chaotic event. After that chaotic event, again, you have a more of a predictable sequence. It's based on momentum, and you get today's moon and Earth pair. But you can't predict right at the moment of that event, but you can predict that the asteroid is going to slam into the Earth, and after it happens, you can predict a lot of what happens coming out through the momentum, but at the moment of impact, you can't. So I want to use this to go back for a second. So I want to now, contrast this chaos with the opposite of chaos, which is, directional flow, you could call it. And in fluids, we use the term, and in fluids, air is also can be a fluid. We call it laminar flow. I'm going to show you a demonstration of laminar flow now. So everybody can see this. This is Destin from Smarter Every Day. Who knows Destin from Smarter Every Day? Anybody? He's a science teacher on YouTube. And we're going to follow him do an experiment. Let me get his... Here, I'm going to turn off his, I'll narrate it. Here, he is using corn syrup in a cylinder, and then he's colored some corn syrup, and he's dropping the corn syrup, the colored corn syrup in, so it's all basically corn syrup, into this vat. And on the inside of this is a cylinder, and on the outside is the lucite cylinder, and it's very sticky. Corn syrup is very thick and very sticky. Sorry about this. I don't subscribe. Okay, good. It's very sticky on the two. So right here, the inner cylinder, the material, the corn syrup is sticking to the central cylinder, and it's sticking to the outer cylinder, and that's what makes the spirals. So we're going to see spirals because it's dragging the insides along and leaving the outsides behind. If you notice, the outside material barely moves. Now he's gone around one time. And this is an experiment that's been done by a number of people. This happens to be the best. I'll let you listen to him now. Can you hear him?
See the spirals.
Can you hear?
No.
You can't hear anything.
3.
Can you hear now?
Is your heart pounding?
Yeah, that's better.
That's amazing. Can you see the spiral in it?
All right, I'm going to turn off his sound. I'm just going to narrow. So he's at, I think, 5 here. And pretty soon he's going to be at 6 rotations. Everybody can see this, right? He's going to be at 6, and 6 rotations is a world record for this experiment. He will go all the way to 7 rotation. So he's in world record territory right now. And see how it's all mixed? It's mixed. It looks chaotic. Chaotic mixing, right? He's going to come all, now he's 6.5. Now he's going to come around. You can see it looking down. It's still separated. And now I'll jump ahead a bit. And now he starts to undo it. So he did 7 revolutions. And now he's starting to undo it. Here it's going to go a little faster. And he's very nervous. He's talking about how nervous he is. He's been working on this for months to build this contraption. And here they're getting down to, I think he's got 2 more to go. And I hope this is about the most satisfying piece of video you see this week, or maybe this month, because he's coming back to the last revolution.
You see that?
And what happens? Now he says, my heart is pounding because he's afraid the red and the blue have mixed. But in fact, if you go 7 revolutions back.
Yes.
Yeah. That's laminar flow. Any questions?
How did that happen?
Is that about the coolest thing you've seen all week? What?
Yeah. That girl doing the thing. Do you think that has anything to do with that?
And if you want to share this, it's Smarter Every Day. I'll put the now that everybody's seen this, I'll put the link to this in the community. Does everybody understand? This is predictable, modelable. There's no chaos here. Any reactions, questions? Is it a trick? No. Anybody? No? Everybody just saying, okay, no problem. Check. Next.
Explain.
Okay. Who wants to explain this?
You should.
Oh, somebody else can do it. I'm being lazy.
You should
Who wants to take it? This is laminar flow. There are many videos on laminar flow. He loves laminar flow. He's done many videos on laminar flow. And it's not chaotic. There's no chaotic mixing. It's fully laminar. And so if you back up the corn syrup, it works. Doesn't work with water. Water's going to have chaotic drift, right? But the corn syrup is thick enough to take that out, so that it's just laminar flow. And if you're interested in this, type laminar flow into Google, into YouTube. You'll see many, many videos on laminar.
But how did she write the name?
What? Oh, you're talking to somebody else? Not to me. All right, so let me go to the next one, which is back where we were last week. Most people will remember this. This is the Earth at 90 million years ago, very hot. Remember, everybody, that we have equatorial flow here. We have a big equatorial current. The Earth spins eastward, right? Ever eastward. And as it goes on its journey, oops, I'm not going the right way. As it goes eastward on its journey, yeah, that's eastward. What happens to the water? The water gets sloshed back at the equator. It actually goes around in currents, and then it has to go the other way in the temperate zones. But right here, it's getting sloshed back. And it's that friction of the water against the Earth that is slowing the day down, slowing the Earth's rotation. Look, right now at 90 million years ago, the time of the dinosaurs, this is the late Cretaceous. The Earth, the length of day was 23.5 hours. And so it's slowing down from a very fast 8-hour day 4 billion years ago down, because as it rotates, the water gets sloshed against the sides. That creates friction, generating heat. It also takes some of the momentum out of the Earth. Okay. And so there's this constant westward flow of water across the equator. We went over this last week. You will remember that at 66 million years, we have an explosion of a Chicxulub crater. Remember that? Here it comes. It's a white dot. It's going to be right here, right there. That was the impact of the meteor that killed the dinosaurs, and it had no impact on climate. It darkened the skies and froze everything for a couple decades, 100 years, whatever. And then things went back because of the equatorial flow of water creates our climate, not one event. So actually it had no impact on the climate, over 100 years, it really washed out. Okay, that's not climate. But here, I want you to watch a particular event that I mentioned last time. Here comes India. And now you see the Mediterranean start to close at 43, and it's going to happen right at 33 million years. I'll stop it right there. It closed. Saudi Arabia connected to Turkey and formed the Middle East at 33 million years, and it closed, stopping the equatorial flow westward. And where did it have to go? It had to come down here and around Cape Town, which is why Cape Town has wonderful Mediterranean climate, because the warm water's coming straight from the equator. And that's why Tierra del Fuego is freezing cold, because that water goes straight up here into the Atlantic and doesn't make it down there. This is just still the Southern Ocean going round and around and it's very cold. All that warm water comes back up here and starts to go north and develops into the jet stream. And this 33 million year point where this closes, we can see it in the rocks of temperature. Here's 66 million years ago. This is the time of the dinosaurs and the impact. Temperature went down here. This is the impact right here. Here's the impact of the crater. It only lasted a few thousand years or so. And then temperatures went back up, just mostly because of probably proximity, the sun getting closer to the sun, and then down. And then at 33 million years, we have this huge event right here that drops temperatures and forms ice caps. And that is right here. That is right here when this closes, forcing the water around the Cape of Good Hope, right? Cape of Good Hope or Cape Horn? Cape Horn? Gosh, Cape Horn, I think. Does anybody know? You don't know your capes?
I think it's Good Hope, because I work in logistics and we're having to reroute all the vessels around there.
That's Good Hope. Then this one must be Cape Horn, I guess. Is that right? I don't know. Okay, let's say that this is all right. So the water's coming around here now, and a lot of it is moving up and out to space here. Now, a bunch of it is moving pretty much straight into this space here, this warm water channel that then moves. I have to say this a little more correctly. This is very cold water here, the Southern Ocean. The heat takes to the air at this point, creates storms where the hot and cold water mix, creates storms that move the heat to the poles, to the South Pole. And then the same thing happens with this heat as it moves up. It creates storms, and most of it is storminess over here. 2/3 of the heat is carried in the air, and only 1/3 goes through the water. And it gets to the poles. And this is why we have ice down here. Remember, this is also wrong. This is just, our best guess. A bunch of geologists have put this together. We don't know what's actually happening elsewhere. It's just a guess. But we're about to come to 14 million years ago, and something else happens, and it's actually happening right now. I'll just back up a tiny bit. Let's watch here. Here's 18. Here we're closing the Isthmus of Panama. Is this related to this? No, it's just this is just momentum of the continents. There's no purpose behind any of it. But right there, it closes. At that point, it really starts the Gulf Stream. It also starts El Nino. It starts the Pacific Decadal Oscillation, because that warm water is no longer coming through. And this is the climate regime we live in today. And here it is. Here's that event right at 14 million years is right here. This is the Isthmus of Panama closing. You'll notice that the climate regime changes tremendously. Watch the poles, watch the caps. Here comes the ice. Here comes the ice. Because the heat has a chance to escape. It's no longer trapped near the equator. It has an easier route of escape to the poles. Aha. And that gives us lower temperatures. And notice that CO2 has nothing to do with this, of course. This is CO2 in gray. Okay. And those lower temperatures are all brought on by this continental shift that closed the Isthmus of Panama. And this is all our current regime here. All right, we're going to look more at this in a minute. I've got to start the other unit pretty soon, but I wanted to kind of close this loop and show you the 33 million year event and the 14 million year event. And that is our current climate conditions as set by the shape of the continents. And everything since then we're going to investigate in a few minutes, but I just want to give you guys time to catch your breath and give me any feedback. Tell me if that was interesting, what you learned, what questions, anything.
Based on how that's now closed, is that going to close further and in the long run probably just get colder, do you think? Or is there potentially going to open up in other areas, looking at the kind of the way the continents are going to move, or is it?
It depends on the time frame you're talking about. So now if you're asking me about 10, 20, 30 million years from now, it's a good question, because then you have to talk to someone who predicts where the continental plates go. And there are videos online about where the continental plates are moving. And it's all speculative. In 100 years, we'll probably have a much better idea where the continental plates will go. So on the order of 10, 20, 30 million years, that's a good question. And I don't know the answer. I just haven't studied where, there's a lot of uncertainty about where the continental plates will go and how those ocean currents will change and react. It's a big, hard question. But on the order of, let's say, under 1 million years, or even in 3 million years, the continents don't change much. In 1 million years, a continent moves like 100 meters, 200 meters, something like that. It's just not enough to change the patterns, unless it were some strategic thing, like something closing.
Well, I suppose a sudden comet impact could.
Well, sure, of course.
Things up, or...
That's right. Could change a lot of things, or not, depending on all kinds of things. That's right. It all depends on the details there. That's a chaotic event. So it's all about the details and what's predictable and what's not. Anybody else? Questions? Somebody just tell me, oh, this is absolutely crystal clear. You're just feeding it to me exactly like I needed it. This is just great, not over my head. Or somebody say, oh, you're going so slowly, it's just putting me to sleep. Or give me some feedback here.
It's all good. It's all good for me anyway. Thank you.
About right?
Yeah.
I'm feeding you a diet of reasonable factoids at a good rate. Yeah.
I think seeing your interview with Mike really helped me understand it all. You put it into an hour, and that's what brought me into buying into this and wanting to go further with it and learn about the detail a bit more, and to be able to communicate it with friends and colleagues in just general conversation, and to help unpick and plant seeds.
Sure. Wait till you see how that works out.
Yeah, it hasn't been successful so far.
It's not about climate, and it's not about science. So learning climate science is not where the action is. It's mostly about money. Anybody else, though, on just this last, the way I present, or is it coming too fast? Is it disjointed? Is it holding together for you?
It's good for me. It's really interesting. I'll probably watch it 2 or 3 times to sort of
Okay.
let
Well,
it
there's,
sink in. But it's
I will keep posting videos in the resources section for
Yeah.
further study too. Yeah.
yeah. But yeah, no, it's really interesting.
Okay.
Happy with-
Anybody bewildered or stuck?
Well, I mean, I'll certainly have to watch it again, but
Yeah.
you know, no, it's really interesting. A lot of stuff I don't know.
Okay,
So,
that's fine.
yeah, no, it's good. Thank you.
All right, we're going to go into a new unit now. And this is on temperature, and then we're not going to get even halfway through. Oh, somebody says Simon's mic is not muted, so we're hearing too much. Oh, now it is. It's fine now. All right, so now I'm not screen sharing. I will, let me see here. All right, hold on. All right, good. Let's start screen sharing now. And I'm going to take this for another half an hour, and then if people want to go a little longer, we can. Here we are at something I've been working on for several weeks. It's a pretty big piece of work. I've tried to recreate the temperature of the Earth, the average temperature of the Earth over the last 5 million years, down to a pretty fine degree. And we're going to go on this journey from 5 million years into the present day. And this is going to take an hour and a half or so. So we'll just take it one thing at a time, one step at a time. I'm not going to watch you or look for people raising your hands, so you'll have to just interrupt me if you have a burning question. Okay. All right. Here is a pretty good graph of temperature over the last 5 million years. And notice there are no units because nobody knows the units. If you put in units here and you put in uncertainties, and it all just grays out pretty quickly. And I'm just trying to give a relative idea of what's happening. All right. So just at this level, what do you notice at the 5 million year level? Well, what can you tell? You can tell it's kind of tight in here for 1 million years. It gets a little looser for a while. There's a little less jumpiness for a little while. It gets kind of regular in here for a while, right? And then something interesting happens. First thing we notice, I'm just going to go in. First thing we notice here is that from 3 million years, and the ice cores really go back about 1 million years. So everything out here is rock cores and sediment and, various kinds of interrogating the rock layers. What we notice, first of all, is that temperature goes down gradually for a couple million years. And then about 1 million years ago starts something new and different, right? It's hard to call this momentum. Something changed, right? But what was it? And the answer is we don't know. Nobody really knows. This is called the mid-Pleistocene transition. That's what this is here for. And the key here is that the driver of temperature depends on the time window. That's why I asked Joe, about the continents moving on the order of 10 to 20 million years, 30, 40 million years. Yes, we should talk about the continents moving. On the order of 1 million years, we should not. So the driver of temperature depends on the time window. And over this period of time, which is, 1.5 million, 2 million years, it gradually went down and then it stopped going down and we don't know why. And then it started getting more. Remember, this is the same scale. So you're not zoomed in over here at all. This is all the same scale. So something really changed here. This is called the mid-Pleistocene transition. If you have Javier's book, you can look it up. If you have it on Kindle, you can just type in mid-Pleistocene transition. And you can there's lots of stuff online about it. Probably at least half of that is wrong. But mostly things changed. We're not sure why. And we started something new. And you've probably seen this graph. Probably Al Gore showed it to you to show you how CO2 drives temperature. But some people realize that's not true. Some people realize that temperature drives CO2. drives it into and out of the ocean as it rises and falls. This is high temperature here. And I'll just get a little friendly tool here. I'll just get a line tool, I guess, and I'll draw myself a line. Whoa, that's not a line. Here's a line. Oh, okay, forget that. I'm just kind of messing around. Okay, when I have a line like, oh, that's not, yeah, okay. Just put it here. Whoops. If I have a line like this, and if I put it here, I'm going to turn that off. If I put it here, this is kind of the hot times, the warm times. These are called interglacials, because for the last million years, we've been in a cold period. We have been in a pretty cold period for 33 million years, right? We're in an ice age now, and once in a while we pop up out of the ice age and the ice caps melt for a couple of 1,000, 120, 10, 20, 30,000 years. And then we go back into the ice age again. This is all ice age. And then down here, we're really in a frozen time. These are called the glacials, where glaciers take over the land masses. And in Canada, you may be aware, New York City 20,000 years ago, and that's right here. 20,000 years ago, New York City was under a kilometer of ice. Boston was under a mile of ice, and Quebec was under 2 miles of ice. That's the Laurentide ice sheet. And I think something similar must have happened to mainland Europe. I don't know about the UK 20,000 years ago, but it was very, very cold. And ice sheets went way down into the middle latitudes. And the equator area was warm, but not as warm as it is today. So then things came back up in the last 1,000 years. I'm going to show that. But what is driving this up-down motion? That's what we're here to discuss. How many people here have looked at and studied a bit of Milankovitch theory? This is called orbital mechanics of the sun and the earth. And this is going to take some time, and I will go into it today and we'll revisit it next week. And so the first one I'm going to talk about is eccentricity. The three where am I? Got something running interference here. The three, oh, I see. It's over here. Determiners of the temperature and the orbital mechanics. Oh, great. I don't. Oh, where did I put it? I'll find it down here. Sorry. Oh, great. I'm not prepared, obviously. Let me do it without then. Actually, I do have it right here. I put it here. Here they are. Can everybody see this? I put this into the community. Can everybody see Milankovitch cycles? Yes? Okay. So the three are eccentricity, obliquity, and precession, which I had my kids memorize since they were 6 years old. Eccentricity is the roundness of the Earth's orbit around the sun. The roundness, it's never round, it's always in an ellipse. But when it's really, it goes back and forth. And when it's close to round, it's really close to round. And right now we're pretty close to as round as we can get. And the difference is 3 million miles of diameter. So it's only 1.5 million. Actually, I think it's 3 million miles in radius. So we're at 93 million miles now, and 90 million miles in January. Something like 93 million in July and 90 million in January. It's not quite true, but it's an order of 3 million miles. It's less, it's about 3%. Think of it that way. And the rounder it is, let's go back. The rounder it is, the colder it is. The rounder the orbit, the colder it is. I'll explain that in a second. And so here we are at practically round. These bottom points are practically round. Yeah. Practically round. And at those times, there are some deep troughs in the temperature cycle. Now, you're going to say, okay, yeah, but not always. And that's true. Look right here. It's really, really round, super round here. And it's not very, and it's very hot there. So I'm going to explain that in a second. You know, when you're at the beach and you see a wave coming in every minute, but you know from looking at the waves that the waves come in waves. After an hour or two, there's a number of big waves that come and they build up. And then after some period of time, they die down, right? And that's what we see with eccentricity. We see sometimes these cycles of round to elliptical are more or less. And then they go down to very round, and then they go up to very elliptical. And generally, when it's very elliptical, you see that temperatures are very high, right? Here it's very elliptical. Temperatures are very high. See how that correlates? When it's more elliptical, temperatures are very warm. Why? Why? What is going on? This is the concept of a window of opportunity. So that when the Earth is going in a near circle around the sun, here I have a sun. I got a sun just for this occasion. When the Earth is going in a circle, the sun doesn't have much of a chance to break the ice. We're in a regime where ice is preferable. It's cold. It's trying, because of the continents, it's trying to ice up. And the Earth, when it's circular, doesn't have much of a chance to eat away at the ice. There isn't enough time, there isn't an opportunity to take the ice away. Whereas when it's highly elliptical, like this, when it's elliptical, there are times when, and we're talking about, you know, hundreds of thousands of years, when, because we're so close, the sun has a chance to start melting the ice and make progress against the ice. So that year after year, you know, it's half a meter or it's a meter more every year. And then that creates less albedo, and that has a feedback that warms and warms and warms when you're close. And then when you go off far away, and this is a yearly cycle, right? It just happens to be very elliptical. It's a yearly cycle, but as we come through summer, we have more intense heat to chip away, and then it goes off into very deep cold. So when we have high eccentricity, we have very cold winters and very warm summers. We haven't had this for, you know, 500,000 years or whatever, right? We can look. We haven't had this for 100,000 years or so. Oops, this is the high, very warm summers and very cold winters, gives the ice a chance to melt. And when the orbit is almost always as round as it can be, there's no chance to break that ice. The ice just keeps accumulating, and there's no hot enough summer. There isn't enough energy coming in at summer to make progress against the ice. And that gives us these cold periods when it's more round. And if you notice, it's every 100,000 years, there's a cycle. This is the 100,000 year eccentricity cycle, where it gets very low. So there's two things to notice. First of all, when it's very elliptical, when it's high, there's almost always a warm period. Okay? Almost always goes up. temperature goes up. When there's a warm period, temperature is going up. Okay. When there is a cold period, that's a mostly circular, it's almost always dragging temperatures down. So here, as we come down towards circular, we're generally dragging temperatures down. Here, we're dragging those temperatures down. We're dragging temperatures from the peak down. And that's because it's getting more round and the summer doesn't have enough chance to make progress against the glaciers. Here is going down toward round. We're always losing heat. As it goes down toward round, temperatures are always falling. And yet, when it's all the way down, we don't necessarily have a bottom. It doesn't follow exactly, right? Fine, we're going to learn more about that. In fact, you can predict that the next one will be down even more because we're coming to the end of the cycle here. And yet, that down cycle may not produce super low temperatures. We will see. Right now, we're right here. See this black line in temperature going up? But we've seen many of those. This is nothing surprising. This happens all the time. Look, one more thing to mention here. Temperature goes up fast and down and cools slowly. That's because of feedbacks. It takes a long time to get rid of the heat and it cools slowly. See, it almost always goes up fast and cools slowly. And that's actually true on a smaller scale, we'll see as well. So that's eccentricity. The next one is obliquity. Who knows what obliquity is?
Was it tilt?
It's the tilt. It's the tilt from 21.5 degrees is as upright as we get, and 24.5 degrees is as lopsided, turned over as we get. And like a top, the Earth is wobbling back and forth through different degrees from 21.5, 21.3, I don't know, to 24.5, 24.6, something, I don't know. So the obliquity turns out to really matter. And the obliquity, again, let's look what's going on with obliquity. When obliquity is high, that means the tilt is greatest. When it's high, when it's up. When it's down, that means the tilt is minimal. And once again, the tilt gives more access to the Arctic to melt ice. It's more of a chance to break the ice regime and start winning against the ice and beating it back. And that provides more and more of that, and that gives us better temperatures until the momentum of the wobble brings it back upright. And when it's more upright, there's less what we call insulation, less energy arriving at the poles during summer. It's a shorter summer. It's a milder summer. And that brings, when it's low, that brings temperatures down. Temperatures down. So we say obliquity is on this scale of, hundreds of thousands of years is a huge driver. You've got to overlay it with the eccentricity because they work together, so that when both are down, you tend to get low temperatures. Here, one is down and one is up, and yet temperatures came down a lot. So there's more to it than that. I'm going to explain that in a second. Here, both are up. This is eccentricity is up, obliquity is up, and temperatures are way up. That's a spike, right? What do we have today? We're just starting down in eccentricity, and we're on the way up in obliquity. Obliquity is increasing. Take this off my wall, which is next to my bed. And we can see eccentricity is going down. We're heading toward a low eccentricity phase. This is a graph you can find online. I'll post it in the resources section. Okay. Obliquity is peaking. This is today, right? If I'm reading this correctly. Yeah. So obliquity is on the way down. That means we are getting toward less tilted over and more straight up, less obliquity, more straight up. That's colder. This points toward colder. This points toward colder. Okay. Then we have precession, which I'll explain in a second. Then this is the heat coming in summer, the summer heat, the number of hot days in summer. And you can see we passed it 10,000 years. Is this 10,000? Should be, yeah. We passed it 10,000 years ago. We're going to see that in a minute or next week probably. And now we're, it's on the way colder. We've got fewer hot days in summer here. So I'm going to go to this one next, but you can see that these things combine more or less, but they occasionally skip a beat. And this is, so here's a good example of eccentricity down, obliquity up, and it gives you a middle temperature regime. Okay, no spikes. Right here is obliquity is pretty far down. So, I mean, eccentricity is pretty far down, but obliquity is pulling up really hard. So one is pulling down, one is pulling up. And in this particular case, obliquity wins. Here, obliquity is pulling up, but eccentricity has pulled down a lot. And so you can see this isn't the whole story, right? It's a lot of it. These are two big puzzle pieces that work together that often give you the result you might think. Here's both are down and temperature is down. Here's low eccentricity, and it overcomes the obliquity. This is rare. Obliquity is usually more prominent. So this is very rare. What's going on is you've got other planets like Jupiter and Saturn that are huge that also pull. Just take a second, everybody. The solar system, all the planets rotate around what?
Sun.
No. I don't ask simple questions. They rotate around the barycenter of the solar system. What's the barycenter? I will put a video about this, but they rotate around the center of mass of the whole thing, of everything combined, which is not the center of the sun. In fact, if you measure it, it's somewhere toward the edge of the sun. So the sun is also rotating around the barycenter as the other planets pull it in different directions. And at different times, some planets are lined up. And so the barycenter itself makes this little complicated path that I'll show you in a video. It's pretty cool. And the barycenter is this focus of the ellipse that the Earth goes around. So the Earth is in an ellipse. An ellipse always has two foci. And the first focus is at the barycenter. And the second focus is out in space somewhere. So you can probably see that right here. Oops. The barycenter is, let's say, right here. It has to do with where's Jupiter and where's Saturn, because those are huge. So, it could be here, right? And the sun, and this dance of all these planets is the only thing that's not moving is the barycenter. And the Earth is going around the barycenter as a focus. And then the other focus is somewhere out in space. Don't think it has any particular, meaning for us. But this dance is very complex. And in fact, the Earth not only stays in the plane, but once in a while, the Earth wobbles up and wobbles down at different angles to the plane. So that causes more inputs to this equation. So it's not 100%, but you can see it's pretty useful to understand this. I mean, you could see why Milankovitch got the Nobel Prize in 1920 something, because this is a super useful model, right? And then the final one is precession. And I'm going to take enough time to do precession, and then we'll draw this to a close for today. Precession is the wobble of the axis. So obliquity is the angle, and precession is the wobble. It makes a trip around sorry, I didn't mention the obliquity cycle. Eccentricity cycle is about 100,000 years with a 405,000 year wave cycle. Obliquity is at 41,000 years. 41,000 years from, low, 41,000 years of obliquity. So it's every 41,000 years. This period is very regular. The amplitude is not, the period is. It's 41,000 years changing the angle. All right. And then the precession is the rotation around. And there's no low or high here. I'm going to try to do this and do a better job than I did the other day. This is a little tricky because we're at an angle. So let me see if I can do this. In July, I never say summer because the two hemispheres have different summers. In July, the Earth is farthest from the sun at this angle, okay? And in January, we're closer, but it's not our summer anymore. It's our winter, okay? So in July, the planet as a whole is coolest. Oh, I'm sorry. I have to reset. In July, the planet as a whole is warmest. Warmest in July. The whole planet is hottest in July, even though it's winter for the Australians. And in January, the planet is coldest. And in fact, there's a 3.8 degree difference for the whole planet. 3.8 degrees. So when the United Nations tells you 2 degrees, we're all going to, die. Well, it's 3.8 every 6 months. So, you got to wonder about that. When we go back to January, what we have, you can see, is very hot for Australia. Very hot, right? And when we go back to July, we have a hot summer, but it's milder than it would be if we were closer, right? So for the Northern Hemisphere, it's tempered. It's milder than it would be if the places were exchanged, right? In fact, if you think about it, Australia gets very hot summers and very cold winters. Whereas the Northern Hemisphere, here's you guys in Europe, the Northern Hemisphere has milder winters and milder summers. We're closer now, but we're in winter. Now, why is there a difference of 3.8 degrees? Anybody? The whole planet is 3.8 degrees hotter right now than it is in January. Why? Because of the
eccentricity.
No, because this is really just regular. Nope. I've given you all the information you need. The key thing you're missing is the land. There's more land up north, quite a bit more land. And that packs ice, and the ice stores heat. And so there's more ice buildup, and that creates more colder surface temperatures by distributing colder air all over the earth. And as we get into wintertime for us, it gets colder because we have the most influence.
So it's thermal mass then?
Yeah, it's thermal mass. It has to do with where are the continents, because that's where the ice builds up. So it's coldest here, and then what's happening here is we're melting more ice. Antarctica ice never melts. Okay, it's not melting now. It hasn't melted in 33 million years. So get used to it. It's not melting. It's not going anywhere. And here the ice does melt, and the sun can make progress against the ice, and it does so in a mild way. Now, what's going to happen is that this is a 26,000 year cycle. In 6,500 years, which is not that far away, it's going to be like this. it's going to be tilted this way. In another 6,500, in 13,000 years, it's going to be the exact opposite. I hope I got it opposite. I think I do. It's going to be the opposite, so that in 13,000 years, it will be extreme hot summers on Earth, and the whole temperature of Earth will be hotter because we'll be making so much more progress against those glaciers, against that snow, that it will be accentuated up here. And it will be, when it comes around here, it'll be again colder, much colder winters and much hotter summers in 13,000 years from now. And sure enough, 13,000 years ago, we had exactly that situation. We're going to see it next week. We're going to talk more about it. But do you understand? This is the effect of obliquity. And then in 15,000 years, 20 or 18,000, whatever it is, it's going to be tilted over here. And then, of course, in 26,000 years, we're going to be back to this, like it is now, every 26,000 years. So this is what a year looks like now. And this is what a year will look like in 13,000 years. So at that time, Australia will have the buffer zone. Australia will have the cooler winter and the colder, their cooler summer at that time, and their warmer, let me see, let me get it right. This is going to be, we're going to have hotter summers up in the north and colder winters. And then they will have buffered and mild summers and buffered and mild winters because we're closer to the sun now. So then when it comes down to their daytime, we'll be closer to the sun, but they'll still be in winter. So right now, the northern hemisphere has the most extreme and the southern hemisphere has the most mild conditions. And in 13,000 years, that will reverse. And so we don't have up and down in precession. We have, however it is now, which is, which we're in here. Let me go here. And then 13,000 years later, it's the opposite. So you can call it whatever you want. High degree of precession is kind of just a made up name because it's always the same angle. It's just a different orientation to the seasons. The seasons are what change when precession changes. And the distance to the sun is really determined by the eccentricity. So if you think of precession is really a modifier on top of eccentricity. It's a pair. They work together. Precession doesn't do much by itself. It modifies the conditions here. And to make things more complicated, just like a spinning top, precession goes at different rates. So it can have, it can go, I don't know what more precession means and less precession means. I think it maybe goes slower and faster. I'm not sure. It's similar to a top. It's every 26,000 years. So the answer is, I don't know what more precession means. Maybe someone can do some homework and try to figure that out. Why does precession vary? What does that mean? I don't know. I'm happy to say I don't know. That's the only way you learn anything. And so we will go much more into this. This is going to be our home for the next week or maybe even two. I'm not sure, to see what the drivers are. And that the one thing I want to point out is that we talk about, here they all are, all three of them. We talk about being pretty much drivers at this level, but there are missing beats, we say. And so here's a missing beat where it doesn't conform to the eccentricity, but other times it does. Here's a missing beat. And the missing beats just have to do with all kinds of other things in the orbital, in the trajectory of all the momentum that I keep talking about. And there are papers written about what causes the missing beats and what fills them in. And Javier in his book goes really deep into it. So I assume that for most people, this is plenty of detail. You don't need more than this. And the take-home message is that they work together, they work against each other. It's complicated, and much of it is correlated, and sometimes it doesn't give you an easy prediction of what the temperature will be. I'm sure there are questions about this, and I'm going to put some videos in the resources section on this, so you'll be able to get this a couple times. And there's a very good one already in the resources section, so check that. Any questions though on that, just kind of at the high level?
I think I'm a bit confused on eccentricity having 2 cycles. So I'll probably have to get my head around that by reading a bit further on
Eccentricity, eccentricity is roundness. Right?
Yeah, I get that part, but it's the fact that it said there was 100K year cycle,
it has
400K year cycle.
Because it comes in waves. It comes in waves. It peaks and then it goes down. And so it's a 405-year cycle. And it's pretty, that part is pretty simple. This is 405 years. This is a wave of waves. And here's another one. And it really is 405,000 years. It looks a little hard to determine on this, but it's basically, think of it as 100,000 years from trough to trough and 400,000 years from big trough to big trough.
All right. Okay. I get that.
Yeah. Okay. What's causing more precession and less precession? I don't know. I'm interested I'm going to have to, somebody maybe can try to help figure that out. I'm not sure. I don't know what more precession means, because the angle is determined by obliquity. That's nothing to do with the angle.
I'm thinking
the distance is determined by eccentricity. So what does more precession mean? It's not changing the rate, because the rate is always 26,000 years.
When you said it's a type of more of a vibration or a kind of 3-dimensional movement on the axis, so more of a kind of spinning within. Yeah.
I've looked at this 1,000 times and I just realized I have no idea what that means. Anybody who wants to take it as a homework assignment is welcome to. Precession. Anything else? I mean, just at a high level, does everybody get the basics here? That it's complicated, but there is a lot to it at this time resolution. Not in the context of 500 years, no. But in the context of a couple thousand years, yes. This stuff is changing pretty slowly. And in 500 years, we'll have moved a bit, but this is 10,000 years. So every 1,000 years or so, there is enough of a difference here to be influential. But other things are bigger influences at shorter time scales. That's what we'll learn about next week. Makes sense. So we kind of have, there's different scales. One is galactic movement, we talked about last week. Movement through the galaxy. There's a 150 million year galactic cycle that we can see in the rocks. We can see that in the sediment cores. 150 million years. Then we can see that 33 million and 14 million years, there were plate tectonic events that are driving the temperature a lot. And then at the cycle of 400,000 years, we have a super cycle of eccentricity. 100,000 years, we have a single cycle of eccentricity. And then down into the 41,000 year cycle of obliquity, we get a lot of influence from obliquity every 41,000 years. It's going to wash out at 200,000 years, but it's going to be super important if you just talk about the next 2,000 or 3,000 years. Obliquity is going to be your main thing. Next 5,000 to 10,000 years, obliquity is going to be the main thing. But next week, we're going to learn something interesting about precession too. So it's just to whet your appetite and set the stage. So next week, when I talk about these things, they won't be completely foreign. Anybody? You're completely confused. You're not looking forward to it because it's just not so interesting. You're what?
So we're going in 30-year cycles. So how's this going to look in, say, 2050?
Take that, wait, save that for next week. I'm cutting this off at 26,000 years right now.
Oh, okay.
That's where we've stopped, right, at precession. So not more, not less than that. Anybody else?
Just on the eccentricity side, the two cycles.
Eccentricity and obliquity, the main ones.
Yeah, no, just on so the was it the 400,000
Yes, the super cycle
versus the smaller ones? What's the difference between them? Is it just that
it's just a spinning top. It's just a spinning top that happens to get closer and farther and closer and farther, and sometimes it gets farther and then well, it's rounder and elliptical. So it gets more elliptical and then rounder, and then even more elliptical and then rounder, and then really elliptical and then rounder. Or it gets super round and a bit of elliptical, and then less round and a bit of elliptical. So that it's just a spinning top. It's just the kind of thing you can easily model and easily predict. It's very easy to predict the eccentricity of the orbit for the next, millions of years.
Okay.
That doesn't predict our climate, but it's the base on which everything else is, it kind of, like we say a lot, it gives you the window of opportunity. If eccentricity is high, it gives you an opportunity for high temperatures. If it's low, that opportunity is shut, generally. That's really a helpful concept, is these windows of opportunity. We'll see more about that. It's the same with obliquity. Again, obliquity, if obliquity is high, you're going to have higher temperatures most of the time. This is very rare that you have high obliquity and low temperatures. That rarely happens. Something else is working against obliquity for that to happen. And sure enough, something else is. All right, class, pretty good. You're hanging in there. If you're terrified, that's all right. You watch it a couple of times and part of it is the terminology just doesn't slip off the tongue easily, right? So I try to get it right, and I think I managed to do it right, but I've been doing this for years, and it's just the practice. It's easy to screw up and use the wrong term. Anything else? Anybody? I'll stop the recording.